Here we are on page 2 of the functions addendum. Prove that the sum of two even functions is an even function. Okay, remember that the way we prove that a function is even is we put the opposite of x into the function, and then we show that that is the same thing as the function itself. Okay, so we know that an even function has this characteristic. So we're going to start with this. We're going to say, okay, we're going to take the sum of two even functions. So basically what we know is these statements are both true. That if you take the opposite value of x and put it into the function, you're going to get the same thing as the original function for both f and g. So let's take the f plus g function and then put negative x into that and see what we get. Okay, so if we put negative x into f and we put negative x into g, we're going to end up with that. And then, but we have here on the side two relationships which are going to tell us that actually f of negative x and g of negative x are both equal to f of x and g of x respectively. So we could rewrite it as that. So basically what we found is that the opposite x value when plugged into the sum of these two even functions gives you the original two even functions added together. So that, remember, is the characteristic of an even function. When you put in the opposite of x into it, you get the same thing out. So that, therefore, it's proven. Okay? C, the product of two odd functions is an even function. Okay, so remember that the characteristic of an odd function is that if you put the opposite of x into the function, it's equal to the opposite of the original function like that. Okay? So let's take two functions that are both odd, f and g. I'm going to call it f and g again. I hope that doesn't confuse you. And I'm going to multiply them together. Okay? And I get that. Okay. Now, if I put negative x into each of these functions, I will get f of negative x and g of negative x, right? But if I do that, I can take the relationships that I know over here. Both of these are odd functions, so I know that these two relationships work for both. So I'm going to replace f of negative x and g of negative x with negative f of x multiplied times negative g of x. And if I multiply that out and simplify it, the two negatives multiply and become a positive, so I end up with f of x and g of x, which is the same function I started out with. So that is the characteristic of an even function. If you put in the opposite of x into an even function, then what you get out is the original function, and that's what I got here. So therefore I've proven that it's also that two odd functions multiplied together are an even function too. Okay? Alright, now let's do section G. If you do page 70 reading, you can get the answer for this, or you can just listen to me talking here. When solving inequalities, you must find all values of x which make the inequality true. Okay? You can't just find one value, you need to find every single value. So here's an investigation. John was solving this inequality here. And his method was this. 3x plus 2 over 1 minus x is greater than 4. He is going to multiply both sides by 1 minus x. When he does so, the left side becomes much simpler, only the numerator. The right side becomes 4 times 1 minus x. You distribute the 4, you get 4 minus 4x on the right side. 3x plus 2 on the left side. Now, we are going to group the x terms on the left, so 3x plus 4x becomes 7x. The right side becomes 4 minus 2, 2, okay? And then we divide both sides by 7, and we get this answer. X is greater than 2 over 7. Okay. Sarah pointed out that if x equals 5, and she puts that into the original equation, she ends up with, if you put 5 there, and if you put 5 there, you end up with 17 divided by negative 4, which is equal to negative 4 over 4, negative 4 and 1/4, and negative 4 and 1/4 is not greater than 4. Okay, so that's weird, right? Because x equals 5 is in John's solution set, But Sarah could think of a counterexample which would ruin his answer. Okay. And this brings up that age-old rule that if you divide or multiply both sides of an inequality by a negative number, then you need to invert the inequality. Okay, so for example, if you have a really simple statement like 3 is greater than 2, I'm going to multiply both sides by negative 1. The left side becomes negative 3, and the right side becomes negative 2. Now, after multiplying both sides by the same number, negative 1, if I say, no, I don't need to do anything to the inequality sign, look, I've just created an untrue statement where negative 3 is not greater than negative 2, right? Another way of looking at it is if you're on a number line, when you multiply, if you have like 2 and 3 here on the number line, and like 3 is obviously bigger than 2, right? If I multiply both 2 and 3 by negative 1, look how 2 gets reflected to the other side of the number line. 3 also gets reflected to the other side of the number line. Now, do you see how, like, the 2 before was on the left side of 3, the negative 2 is on the right side of negative 3? So do you see how, like, multiplying by negative 1, which is basically a reflection across the middle of the number line, requires you to invert the inequality because you have made all the left numbers into right numbers, etc. Okay? So in this case, there is a point where John divides by, not necessarily by a negative number, but something that could be a negative number, right? Remember, or he like multiplies both sides by a possible negative number. So he multiplies both sides by 1 minus x. 1 minus x, depending on the value of x, could be negative, right? So for example, Sarah putting in x equals 5, if you have x equals 5, 1 minus 5 is negative 4. So in this case, you would actually be multiplying by a negative number. So in the case where 1 minus x is less than 0, which is, some cases, about half the cases, then you would need to make another calculation where you are reversing the inequality. Okay, and then you would end up with another inequality which shows the other part of the solution. Okay, just to show you real quick what it looks like, I would have, in this case, I would have 3x plus 2 is less than 4 over 1 minus x because I've reversed the inequality. Then I complete the rest of the calculation, and I end up with x is less than 2/7. Okay, so in the case that 1 minus x is less than 0, then it's like pretty much the opposite is true. Okay, so when is 1 minus x less than 0? Well, to be more specific, 1 minus x is less than 0 is the same thing as x is greater than 1. So for x values greater than 1, this is the answer. Now, if x is less than 1, then it would be this answer. Okay? All right. Page 71 reading. What are the steps to finding all the solutions to an inequality? First, make the right-hand side, RHS, 0 by shifting all the terms to the left-hand side. Fully factorize the left-hand side. Draw a sign diagram for the left-hand side. Determine the values required for the diagram. Okay, so see example 13. The solution set x is expressed as a sign diagram below. Represent the solution using notation square brackets. You may also use round brackets if you learned it previously. I'm not going to talk about round brackets. I'm just talking about square brackets here. Okay, so in this case, we found 2 critical points, which are -2 and 1/3. And then we've tested the intervals in between them, and we found that this interval is positive, this interval is positive, and this interval is negative. Here I've written the original problem, and here I've written the factored form. So we can see that this solution here, what we're looking for is when this multiplication is greater than or equal to 0. So basically this part and this part are the solutions, And we are including the critical points -2 and 1/3 because those values give you exactly 0 and it's greater than or equal to 0. So what we're going to do is, what we want to do is we want to express this interval and this interval in the notation here. So basically what we're going to say is, first we're going to do the left interval. So the left interval says that basically x is less than or equal to -2, and we can express that by using the brackets. First of all, we use the brackets facing away from the negative infinity, say that we don't actually include the negative infinity value. We do include the -2 value, so then we include it with the square brackets facing the normal way. Now, the other interval, this interval here, one of the critical points is 1/3. The other critical point is infinity. We don't want to include infinity in the interval. We do want to include 1/3 in the interval. So that's how the square bracket notation works. Okay. Page 72, example 15. What TI-84 functions and buttons do you use to graph the LHS and the left-hand side and the right-hand side expressions as two functions and find their intersection points? Okay. So in example 15, you're solving this inequality, and instead of doing what we usually do and grouping like terms and expanding, etc., and then figuring out what x critical points are, we could just figure out when these two functions intersect each other using the calculator, and those would be the critical points, and then we can visually see on the calculator when the left side is bigger and when the right side is bigger, right? The way you're going to do that is you are going to simply type each one of these commands into the y equals screen. So in the y equals screen on the left side, I'm going to put it in the y1, so be careful. I think that there's two ways to do this. One is to put it in parentheses. So I need to put parentheses 3x plus 1, right parentheses, divided by, left parentheses, x minus 2, right parentheses. And if I don't put parentheses around the numerator and the denominator when I put it into the y equals screen, there's going to be trouble, because if you write it all out horizontally, 3x plus 1 slash x minus 2, look what becomes a fraction. 1 divided by x. 3x is not part of the fraction. Minus 2 is not part of the fraction. So be super careful. There's another way to do it, and basically it allows you to make like a vertical fraction like this. Remember, vertical fractions are different than horizontal fractions because vertical fractions have the left and right parentheses implied on the numerator and the denominator. So once you make the vertical fraction, the calculator is going to do the top by itself, it is going to do the bottom by itself, and then it's going to divide them. So it implies the fractions around the numerator and the denominator. So how do you make a vertical fraction? You go to math, you go to number, and then you go down to the end of the list, and there's something called n divided by d. Okay, and then it makes a little fraction thing. And then here you're going to put 3x plus 1, and you're going to put x minus 2. Okay, and that's the left side. And the right side is going to be 2x plus 6. Minus 6. Okay. Now I'm going to graph. Now that I have the left side and the right side, and y1 and y2 as two separate functions, I'm going to graph them, and I'm going to see when they intersect. So that is one of them. From our experience with rational functions, we know that it's the left side, and the right side is the straight line here. So when do they intersect each other, which would be the critical points? Okay, we're going to do second calc intersect. First curve is the hyperbola? Yes. Second curve is the line? Yes. What's your guess? We're going to put the cursor close to this intersection as opposed to this intersection. We want to find the left intersection first. So the left intersection is 1, -4. 1, -4. I'm going to write that down here. Okay, and the other intersection is this one here. Let's find that. Same thing. Second calc, you got to repeat everything over again. You get really good at this, just doing a few problems. First curve is the rational function? Yes. Second curve is the line? Yes. What's your guess? Now, I want it to find the other intersection. So I'm going to move the cursor close to the other intersection, and I'm going to press enter, and then it'll find the new one, which is 5.5, comma 5. So 5.5, comma 5. Okay, so there's two intersection points. And we can kind of see that, like, from this intersection point to the left, the hyperbola is bigger than the line, right? From this intersection point to the right, the line is bigger than the hyperbola, okay? So if we want to say, when is the hyperbola less than or equal to the line, we would say, okay, the hyperbola is greater here, it's less here, greater here, and less here. So, like, this part would be part of the solution. So, and this point here, remember, was x equals 1. So, we could say when x is less or greater than 1, because we want to the right side of this, so greater than or equal to 1, because we want to know when the rational function is less than or equal to. Okay, and then that would be true all the way up to this asymptote. What is the asymptote here? It would be x equals 2, right? So between 1 and 2, you would have the hyperbola less than the line, but remember, the asymptote doesn't have a value, so we won't include it there. Okay, and then the other part that the hyperbola is less than the line would be this part here, and remember, this part here is x equals 5, so anything like x is greater than 5, and we can say greater than or equal to 5 because we are including the intersection point in it, because it's less than or equal to 2x minus 6, right? And then there's no limit on the right side. Okay, so basically these two inequalities give you all the x values where the hyperbola is less than the line. It would be this part here and this part here. Okay.